We're going to review some basic statements of statistical thermodynamics. So we start with the Zeroth Law. Zeroth Law of thermodynamics. This is leading to the definition of a thermometer, if you remember from our previous discussions. The statement of the Zeroth Law of thermodynamics was as follows. If two systems, so we can have two systems, A and B, let's say, if two systems are in thermal equilibrium, and the meaning of thermal equilibrium is that when we form a thermal contact between the two systems, there will be no heat flow from one system to the other. If the two systems are in thermal equilibrium with a third system, so I have system A in thermal equilibrium with system C, system B in thermal equilibrium with system C simultaneously, then they must be in thermal equilibrium with each other. So this statement is basically saying if I form a thermal contact between A and C, systems A and C, I find that there is no net heat flow from one system to the other. They are in thermal equilibrium. System B and C also are in thermal equilibrium. There is no net heat flow from one system to the other. Then if I were to make a thermal contact between systems A and B, they would also be in thermal equilibrium. So this system C can be a thermometer. So basically I can use the thermometer to measure the absolute temperature of system A and systems B, and if they are the same, then basically I conclude from this measurement that A and B will be in thermal equilibrium if there is a thermal contact between them. So this is the main implication of the Zeroth Law of thermodynamics. When we come to the first law of thermodynamics, and that has to do with the mean energy of the system. An equilibrium macrostate of a system can be characterized by its internal energy. Internal energy mean value is a state variable. It basically tells us the equilibrium macrostate of a system. And for an isolated system, if I have no thermal interaction or no adiabatic interaction of any sort with other systems or the rest of the universe, the mean energy of the system must be a constant, so it is isolated. On the other hand, if allowed to interact with the rest of the universe, the change in the mean energy of the system is due to the heat added to the system and or the work done on the system. So in this equation, W is work done on the system, and Q is heat absorbed by the system. So it's the heat transfer from the rest of the universe to the system. And the implication is that basically this is a statement of conservation of energy. So we find that an equilibrium macro state variable, mean internal energy, can be changed using two transfer variables, the transfer of energy achieved by thermal interaction, transfer of energy in the form of heat, or adiabatic interaction, transfer of energy in the form of mechanical work. So using the principle of conservation of energy in the first law of thermodynamics, I can also measure. So this is going to allow measurements of internal energy and heat in terms of work done on the system, as we have seen in our discussion of measurements of the thermodynamic variables. And let's move on to the second law of thermodynamics. Second law of thermodynamics has to do with the entropy. And in addition to the mean internal energy of the system, an equilibrium macro state of a system can be characterized by a quantity called entropy. Entropy, changes in the entropy ds, is always equal to the amount of heat transferred at constant temperature. This is for infinitesimal quasi-static process, and in any real process we're going to have the total entropy delta S total will be greater or equal to 0. So in any process where a thermally isolated system changes from one macro state to another. So this is basically telling us the evolution of the direction of evolution of the system. The system will evolve in such a manner that the total entropy will be maximized. So the implication of the statement of the second law of thermodynamics is that this specifies for us the direction of a process. Now, the third law of thermodynamics also has to do with entropy, but it's rather the definition of a reference macro state in the discussion of thermodynamics. The third law of thermodynamics. When we decrease the temperature, when we approach the absolute zero plus, the entropy of the system becomes a small constant value, S0, if not equal to 1. So it depends on the system, and S0 is a constant. For some systems, even if you go down to nanokelvins or so, the entropy is still not equal to 1, so it's rather approaching this constant S0. Basically, the implication of this is that T equals 0, absolute 0, T equals 0 Kelvin, basically defines a standard macro state. It's the ground state of the system. So these four statements, zeroth law, first law, second law, and third law, basically completes the theory of thermodynamics. And in this case, I have no atomic models included so far. Now, if I continue this discussion by introducing a statistical relation as well, so we introduce a statistical relation, and that has to do with probability of finding a system in a certain state. The probability P of finding a system in a state R is proportional to the number of accessible states for that corresponding scenario. So I have the entropy for the state R with energy ER, let's say, is K times natural logarithm of number of accessible states omega R, and the number of accessible states is e to the SR over K. So you can think of this as the probability of finding a system with a macroscopic parameter such as pressure having a certain value, and that corresponds to a certain number of accessible macro states of the system. So if the system is in one of those accessible macro states, then the macroscopic parameter has this value. And the probability of finding that value of the macroscopic parameter of the system is proportional to the number of accessible states that corresponds to this scenario. And from the definition of entropy, which is Boltzmann constant times natural logarithm of number of accessible states, you can see that the number of accessible states is exponential entropy divided by the Boltzmann constant. So we find that the probability of finding the system in one of those accessible states is proportional to e to the power entropy divided by the Boltzmann constant. So by introducing this statistical relation into our discussion of thermodynamics, This turns into statistical thermodynamics. And the implication of this is that this allows finding probability of occurrence of certain values of the parameters of the system, probabilities and fluctuations at equilibrium. And we can also form a connection with microscopic physics. This connection is through the definition of entropy in terms of number of accessible states by saying that the entropy is Boltzmann constant natural logarithm of number of accessible states. This has the implication that the entropy of the system can be calculated using a microscopic knowledge. So if you know the number of configurations that give you a possible scenario, then you can calculate the corresponding entropy as well. So if we combine statistical thermodynamics with laws of thermodynamics with statistics, and we form a connection with microscopic physics, at the end we get the most general branch of physics that we call statistical mechanics. So this is just a review of what we have done so far. Just summarizing some of the main ideas of this course. We have basic statements of statistical thermodynamics, Zeroth Law of thermodynamics, that basically states if two systems are in thermal equilibrium with a third system, they must be in thermal equilibrium with each other, where the third system can be a thermometer. So this tells us basically how we can determine what will happen if we form a thermal contact between two systems. And the information we gather from the thermometer, that is by forming a thermal equilibrium with another reference system, is without disturbing the equilibrium, without disturbing the mean energy of the system of interest appreciably. We're getting basically the direction of heat flow. So if the temperature of system A is greater than temperature of system B, then we basically will say that there will be a net heat flow. Whether the heat will flow from system A to B or B to A, that is determined by actually the second law of thermodynamics. We have to check the entropy change for these two scenarios. When the entropy change is greater than zero, the total entropy change is greater than zero, this tells us the direction of the process. So it will basically tell us heat must flow from hot objects to the cold object. The first law of thermodynamics says when we have a change in the mean internal energy of the system, this is due to heat added to the system and work done on the system, and it's basically a statement of conservation of energy. The entropy, as we have shown, the fundamental relation in thermodynamics, ds, small changes in entropy, is related to heat added at constant temperature, d bar q over t. And if you have a process that is not a constant temperature process, basically you have to think in the infinitesimal limit. The process is carried out by forming a thermal contact with successive heat reservoirs with higher temperatures. So slightly higher temperatures until we reach the final temperature. So at each step we have the integral d bar q over T, where we go from the initial temperature to the final temperature. So this basically tells us that the process will evolve in a direction that will maximize the entropy. And the third law of thermodynamics says if you go to 0 Kelvin, if we approach 0 Kelvin, entropy becomes a small constant value, S0, and basically it defines a reference macro state, a standard macro state of a system, which is basically the ground state. So this completes the discussion of thermodynamics with no atomic models included. If we talk about the probability of finding the system in a state R with a certain number of accessible states or a certain number of accessible states omega R that correspond to a scenario where the macroscopic parameter of a system has a certain value R, for example, pressure is PR or energy is ER, etc. Then we have the entropy of the system, K natural logarithm number of accessible states, and the number of accessible states corresponding to that scenario is exponential entropy divided by Boltzmann constant. So the probability of finding the system in a certain macro state is proportional to its entropy divided by Boltzmann constant as an exponential factor. That is basically combining laws of thermodynamics with a statistical relation. We reach statistical thermodynamics. We can form a connection with microscopic physics by including this definition of entropy in terms of number of accessible states as K and N omega, and combining statistical relation connection with microscopic physics and thermodynamics, we reach the broader view of statistical mechanics.